Watch a cricket ball being struck. In reality, it's a chaotic explosion of kinetic energy, spraying dirt, moisture, and grass in every direction. Look at this web of variables. If you try to calculate the ball's exact trajectory by attempting to factor in every single detail, the length of the grass, the brand of the bat, the exact stitching on the seam, the math becomes impossible. You run into the paralysis of details. The natural world in its raw form is incredibly intricate. It is too noisy and too tangled to study all at once. Science provides an active system to deal with this. It acts as a set of filters designed to systematically strip away that noise. By applying these filters, we stop guessing and start building tools that actually work, from basic medical treatments to the GPS systems in our pockets. The first filter is simplification, or what scientists call building a model. It requires a surprisingly counterintuitive step: intentional ignorance. Watch what happens to our web of variables. By deliberately ignoring the grass and the bat, and isolating only the ball's mass, its speed, and gravity, the resulting trajectory arc becomes perfectly predictable. This scales up to the largest objects in the universe. When physicist Meghnad Saha set out to understand stars, he faced a completely chaotic system of endless atomic reactions. He chose to ignore almost all of it. Instead of tracking every particle, he modeled the star as a uniform sphere of hot gas. That ruthless simplification worked. By ignoring the noise, Saha successfully proved that a star's color is directly linked to its temperature. Once you've simplified reality into a model, you have to communicate it. That requires the second filter: absolute precision through a standardized global language. To see what happens when that language breaks down, look at the passenger jet that inexplicably ran out of fuel mid-flight. This cross-section shows the math error in real time. The flight needed 22,300 kilograms of fuel, but the ground crew used pounds instead of kilograms. You can see the resulting empty space. The plane took off 15,000 liters short. The pilots managed a dead-stick emergency landing, but the lesson is clear. Standardizing a unit like the kilogram across the globe eliminates ambiguity and creates a rigid foundation for mathematics. Standardized units serve a highly practical purpose. They are the shared communication protocols that keep global trade fair, prevent catastrophic errors, and keep planes in the air. The third filter is anticipation. When simplified models meet precise measurements, science achieves its most useful result: the ability to see what happens before it actually occurs. A rigorous scientific prediction is entirely different from a guess. Looking at dark clouds and assuming it will rain is a guess. Measuring current humidity and comparing it to historical patterns, that is a prediction based on evidence. This chart shows how we map a predictable, near-term weather forecast. By taking precise measurements of temperature, pressure, and wind, we can plot a reliable trajectory for the next few days. But look at what happens further down the timeline. The forecast splinters. Because weather is deeply complex, tiny, unmeasured differences at the start compound into wildly different outcomes a week later. When a prediction failed like this, the scientific mindset does not reject the new evidence to protect a belief. It takes the new data and updates the model. You can apply this exact evidence-based thinking to your daily life. Take the viral myth that eating food during a solar eclipse is toxic. If you ask what physical mechanism causes this, you realize an eclipse is just a shadow. There is no biological or chemical change happening to the food. The reality filter isn't just for labs. It's a habit of thinking that lets you look past viral claims, evaluate evidence for yourself, and make